Hello everyone. In this video, we are going to discuss how to write a MATLAB program to determine the fault current and voltage in a single transmission line for single anti-ground fault, a line-to-line fault, and a double anti-ground fault. Here there are three cases, and in this video, we are going to discuss only on the first case, that is single anti-ground fault. Let us move on to the actual part, uh, theoretical part of the single anti-ground fault, where the sequence components of the single anti-ground fault are mentioned here. V1 is the positive sequence voltage, and V2 is the negative sequence voltage of R phase, and V0 is the zero sequence voltage of the R phase. This is when the fault is occurring at the R phase. We have taken single line to ground fault. Okay, and it can be seen that if we add these three, that would be equal to 0, because of the R phase is shorted and it is grounded, and the phase voltages for the faulted value is given as VR, Vy and Vb, where the R phase is shorted and grounded. The value of VR would be equal to 0, and the value of Vy and Vb remains same with equations V0 plus A square V1 plus A into V2 for Y phase, and for B phase it is V0 plus A times V1 plus A square times V2. And the fault current is nothing but the R phase current IR, because the fault is occurring at the R phase as per our consideration, and it is given as 3 times ER divided by Z1 plus Z2 plus Z0, and the other two values are taken as 0 since these two are open circuited, and the sequence component, current sequence component I0 is given as ER divided by Z0 plus Z1 plus Z2, and the value of I1 and I2. I1 will be equal to I2, that is positive sequence is equal to negative sequence, and that is equal to the value of I0. And for this, if you want to write a program, and as I've already written the program for these equations, since we have taken we need to calculate the voltage and current values, and we have already taken Z0 and Z1 and Z2 are the predefined values, and we are going to fetch it as an input value, and the value of ER is also fed input to the program. And CLC is to clear the console, clear all is to clear the memory, and we'll be showing how to clear the memory using the clear all function. And A is a component which is constant, and its value is 0.5 plus J 0.866, and we have already discussed in the previous video. Please do go through the previous videos. And the value of I0, as we have marked it here, I0 is equal to ER divided by Z1 plus Z2 plus Z1, and the value of I1 and I2 is equal to the value of I0. And the faulty current, the R phase fault current is 3 times ER divided by Z1 plus Z2 plus Z0, and the same thing we have marked it here. And the value of V1, V2 and V0 are taken from these things, and if we observe, the value of V1 is equal to Z0 plus Z2 into ER divided by Z1, Z0, Z1 plus Z2, and here it is something different. To write this equation, we have taken the LCM of these two equations, where ER into Z1 get cancelled. We'll be left with Z0 plus Z2 into ER divided by Z0 plus Z1 plus Z2. Okay, and the value of V2 is here, minus Z2 into ER minus Z2 into ER divided by Z0 plus Z1 plus Z2. Similarly for V0, minus Z0 into ER divided by Z1 plus Z2 into Z0. The same two equations. And the faulty voltages for the phase values, as we have already mentioned, the R phase voltage will be equal to 0 as it is been grounded, and the other two values are here mentioned. And if you want to execute the program, let us take an example. Before taking the example, we are mentioning CLC is to clear the console. This is the console value. If you write a CLC, here we can see the previous video values are already been uploaded here. If you use CLC, console will be cleared, and if you use CLER, clear all, before entering, you need to check the workspace here. The value of A, I1, I2, B, IN, these values are from the previous program, and if you use clear all, you can see the workspace has been cleared and the memory of the previous data has been moved, and now the MATLAB is fresh to or execute. Now, if you run this program, yeah, single line to ground, and if we, yeah, single line to G, it came now, and now we need to enter the phase EMS of the R phase. Let us assume we are having a 11 kV line, and the phase value will be 11 kV divided by root 3. That would be equal to something near 36350 volt. And enter the zero sequence impedance. Let us assume the zero sequence impedance as J 2.2, and the positive sequence impedance, let us assume it as J 1.9, and the negative sequence impedance, let us assume it as J 3.4. Yeah, let us write this one. We have entered till here negative sequence. The value of A is constant, we have not calculated. The value of I naught value is minus 8.46 into 10 raised to 2I, and the value of I1 and I2 remains same with respect to I naught as we have calculated, as we discussed earlier. And the value of fault current is 2.5 into 10 raised to 3I. And the value of V1 is 4.741 into 10 raised to 3. V2 is minus 2.87 into 10 raised to 3, and V0 is minus 1.86 into 10 raised to 3. And the value of phase voltages are here, Vy and Vb, since the phase voltages are matching with each other, a balanced one. Okay. And here also in the workspace also we can fetch the values, the value of Z0, Z1 and Z2. That's what we have inputted. And the value of ER is 6350. That is the value that we have inputted. And the value of A is also constant. And from here to here, from I0 to Vy is the calculated value, and it will be represented on the workspace also along with the command window. If you have any doubts, please do comment below. We'll be connected.